Okay, well, first, thank you very much for the invitation. I'm delighted to be here. And thank you, Carol, for the opportunity to give this talk. This is my last work, and it is a collaboration with Ana Mastei from the University of Córdoba and Mariela Portesi from the University of La Plata in Argentina. Okay, let's see a little bit of teleportation. First, as an outlook of a little outlook of the results of my work, we obtained the average fidelity of teleportation for an isotropic distribution of input states, which could include, for example, mixed states. Okay, the protocols are two. The two situations in which we could calculate the maximal average fidelity are two protocols, two different protocols. In first place, we have a standard quantum teleportation and an arbitrary resource. And on the other hand, we have something in the middle between the Bell basis and the computational basis. We have another protocol whose characteristics measurement is something in the middle between the Bell basis and the computational basis. And here in the second example, we have as resource of the protocol, we have the set of Bell diagonal states. Through this talk, we are talking about useful protocols, and the definition of a useful protocol is a protocol who can overcome the classical fidelity. I mean, the fidelity, the characteristic fidelity of a useful protocol is greater than its classical counterpart. Okay. Oh, excellent. Well, the key points of the work could be summarized in three conclusions. The first one is in standard quantum teleportation. You can have a useful protocol even when the resource is not entangled, and even more, even when the resource has no quantum correlation. And this is strange. This is a difference from the usual quantum teleportation in which you have pure states. Here we will calculate the maximal teleportation for arbitrary isotropic distribution. All right. Secondly, I'm sorry. It's the distribution does not depend on the direction of the vectors. Depends only on the modulus. Okay. Yes.
Very nice.
T is the Bloch vector of the matrix. We were talking about qubits, and if you have a qubit, you can write it here. You have the Pauli matrices. Okay, this is the Bloch vector of this qubit, and an isotropic distribution of this kind of states does not depend on the direction of the vector, only depends on the modulus.
So the radial distribution, yes.
Can you repeat?
You have a radial distribution which is important, not angular.
Exactly. It is okay. I didn't get. Can you? No, in this case we have a qubit, just a qubit. Okay, we want to teleport this state, qubit states. And well,
so given is only radial distribution, P of R.
Excellent.
And angular is constant.
Yes, exactly. For example, I will give some example of distributions of input states. Well, as a second.
Random pure states, a special kind of class of.
Yes, exactly. Yes. Well, as a second conclusion, we have that if the measurement projects onto a set of states that is not correlated, quantum correlated, for example, the computational basis, the protocol is not useful for any Bell diagonal resource, okay? And finally, if you has another measurement that can has correlations, then the protocol, then you will find always a resource in order to have a useful protocol. Okay, well, first of all, why quantum teleportation? Quantum teleportation is an important procedure for quantum computation, for example, and well, it consists of the transmission of states from one system to another. For example, you have a system A, and you would like to send this state to another system. And here we have quantum or classical stuff. Then, why do we look average fidelity? Average fidelity is the usual and most common quantifier of the ability of a given protocol to quantify the to quantify the score. Basically, the score is how well is your protocol to teleport states. And why we consider mixed state as input? Well, it is experimentally proved, for example, here, that you can teleport arbitrary state. You can teleport anything, not just pure state, as for example, the famous classical score 2/3, in which it's only valid for pure states.
But classical, you mean not with the states are classical?
No. But for example, you have a protocol, a classical protocol, whose average fidelity is 2/3. It's a famous. It is a famous score because it is used to compare when a protocol is useful or not. If your fidelity overcomes 2/3, then it's useful. Well, let's see a little bit the mathematics. And let's consider P a protocol that produces output state rho I with probability Pi. Then for an input given by a Bloch vector T, we can quantify the ability of the protocol to teleport this state using equation 1. Okay, we have here a lot of output states, and here the state we want to teleport. Then we compare this state with this set of states using the quantum fidelity that is given by equation 2.
You only consider qubits. You teleport now only qubits.
Yes, this is true. Yes, I did. Well, this is yes. This is for qubits.
What is this? The small n?
Where is an n is the quantity of output that your protocol could produce.
So it produces output I with probability Pi.
You produce n different outputs. Sorry. Well, if you want a score for your protocol, your score should be independent of the initial state. For example, should be independent of this vector. In order to do that, we take the average, and here is the distribution, the initial distribution of a state that we will consider. Well, let's consider now a step before. Let's say that you have a protocol that produce conditional states. here, given by this matrix. Now, let's say that we have the possibility to perform unitary operations in order to increase your score, all right? Then our final states will be are given by this transformation, and as we know, if you have unitary operations, then the map into the Bloch sphere are rotations, and you get as Bloch vector of your final states given by this. R is a rotation corresponding to the unitary. Okay. Now the fidelity, the similarity depends on two parts, the green and the red one. If we look at 1 second, can we see that we can see that this part is independent of the unitary operations? All right. Then if we want to optimize this quantity or the average of this quantity over optimal operation, unitary operation, then you need to optimize just only this scalar product. For convenience, then we define F tilde and Q tilde, and this will be the quantity that we want to optimize. Okay, the operations that maximize the average fidelity, or equation 6, equation 6, are called optimal operations. Yes.
So these optimal operations, like the corrections happen at the end of the original translation protocol, where you do a 4-item measurement and you like do different arbitrary things.
I'm not sure if I get the question, but you have a protocol. Your protocol first produce these states that are conditional states, and then you have the opportunity to apply unitaries over this state in order to get a better fidelity, a better average fidelity.
But you know the outcome, right? You know this I.
Yes, you know this. You know this result. Only this. You measure. Okay. Some this we have 4 different distributions we consider in our work. First, you have pure states that are the surface of the Bloch ball, and random mixed state. You have the entire Bloch ball. Mixed state with a fixed purity given by X. Here we have a ball of radius X inside the Bloch ball. The surface. Exactly, you have the surface. And a state belonging, whose Bloch vector belongs to a shell of radius A and B. These are our 4 different distributions. And let's first consider our important protocol, that is the classical teleportation protocol. If you well define this protocol, you can say when your protocol is useful or not. Okay, well, this problem was already solved by Vidal. It is Vidal and here in this paper. Okay, well, a classical teleportation protocol consists in choose states according to the result of a measurement and a guessing strategy. Here we have 2 parts. First, a measurement directly on the state. Classically, we first measure here. We take a measurement here. And then, according to a guessing strategy, we prepared the output states. Then, well, we will consider a POVM. And if we want the optimal operation here, well, first, let's see how can we quantify the things. The Alice measurement is given by these numbers here. Here we have the measurement operators, and this is a number, a complex number. And here we have an state given by these block vectors. Then the measurement is defined by these numbers and these vectors. And here is the probability. The Bob guessing strategy will be is given by Ri, these vectors. Then if we want to know which is the best fidelity for this protocol, then we should take the optimization of the average fidelity over these parameters, the measurement and the guessing strategy. Well, Vidal and his groups then already solved this problem, and the maximum is given by equation 8. And we can see that the distribution, the isotropic distribution, it's here. For example, for pure states, we know that the outcome is 2/3, but if we consider the entire block ball, the results is this new one. Let's see now the quantum protocol. In the quantum protocol, we need 3 qubits, A, B, and C. Then here we have a qubit, another qubit. And the aim of the protocol is to teleport the state of the first qubit to the third, C. Then the first steps of the protocol consist in preparing a joint state of these 2 qubits. Here we put rho. Okay. And the second step consists in perform a measurement over the first 2 qubits, A and B. And finally, we have to perform the unitaries over the conditional states that produces the second state, the second step. Okay, when you measure, you have conditional states here over system C, and then you can perform your unitary operation in order to increase the fidelity. This is the most common protocol, perfect quantum teleportation. Here we have a Bell state, and the measurement is a projection onto the Bell basis. If you do that, then there exist unitary operations there exists unitary operation that produces here the state A always.
This is amazing. This perfect quantum teleportation scheme, it works perfectly for pure states.
No, for mixed also.
Mixed also.
Yes.
And it gives always perfect results.
Yes. Yes, we can do the math. It is yes. Well, sorry.
So, let me ask something. In the former slide, you showed that the fidelity to transport state, mixed state is higher than a pure state, right? The 0.
The classical one, yes.
Yes. Do you understand why?
Yes, it is. It is a good question if I understand, but it is well explained in the Vidal's paper, and.
Maybe the intuition probably is because it's a mixed state. It's a smaller, like the fidelity is bigger. Right?
Yes.
If you are very close to the middle, you can just guess any state there. Even if you guess incorrectly, the fidelity will be very close.
Exactly. This is the reason. Excellent. Well, Then we can continue. But our question now is, what happens if we measure a general P of M, taking, for example, this parametrization of the measurement? And here we have for Neumann measurements. Okay, that's the only restriction. And what happens if, as resource estates, this estate is a general one, given by these marginal states and this matrix, this covariant matrix. Then the expressions of the conditional estates are the following. Yes. I forget the summation.
So here we have summation, it goes over.
Yes, it's repetition.
K or L, yes. And then double K.
KL, yes, we have a matrix, vector, vector. Yes, I'm sorry.
So this C and KL is just like correlation matrix.
Covariance matrix, technically. Yes, yes.
And then it corresponds to this TKL in the state law,
yes? Yes, yes. This is, in fact, a correlation matrix.
Okay.
Okay.
And those green and blue are fixed, or you will optimize over them?
For the moment, no, are fixed. Are fixed. Yes. Yes. The question is, what happened with the conditional state if you measure this measurement?
So you have a fixed measurement.
Yes. Yes. And then you take this state as a resource. Then the conditional estates of your protocol, before to apply the unitaries, are given by, and here I forget the summation. Yes. Well, here we have the conditional estate that is given by these marginal estates, and this is the Bloch vector. This is a Bloch vector, and we have here scalar products. For example, here you have the estate you want to teleport. Here we have the measurement, resource, and resource. Okay, well, you can see. Then the Bloch vector of the conditional state can be written as equation 10. Before to continue, we should define first a measure of quantum correlation that it is called fully entangled fraction. You have a bipartite estate and you want to quantify the correlation between the two parts. Well, one well-defined measure is the fully entangled fraction. And it is defined as the optimization over unitaries. Here we have a Bell estates. And well, that's all. Here we have rho is bipartite state.
Well, in short, you look for such a maximally entangled state which gives you the largest overlap, so maximal fidelity.
The maximization is over the unitaries.
Yes, but changing unitaries.
Yes, yes.
Family of all locally equivalent maximally entangled states. Yes?
That's correct. Yes, that's good. Well,
so of course, if rho is one of maximally entangled states itself, it will be one.
Exactly. Yes. We can keep in mind this sentence.
Even if rho is maximally mixed, of course, it will not be zero. It will be the worst case, like it's maximally mixed. It will be like 1/2 or something.
Well, okay. Then the general teleportation protocol, I mean the standard quantum teleportation protocol depends on this quantity. How? As follows. Here we have the score, the maximization of the average fidelity over pure estates. If you take this and you take the maximum over your possible unitaries, then you will get that your fidelity is given by this equation, and here you have the fully entangled fraction. This equation justifies the names justify the name of rho, because your score basically depends directly on the quantum correlations of your state, and it is here. Well, there exists a general rule in quantum teleportation. If you teleport pure states, the general rule is that your protocol will be useful only if your resource state is entangled. If you put here an entangled state, then this quantity will be greater than 2/3. Then our problem is to find the same maximum, but inserting here an isotropic distribution in general, and measuring a general measurement operators and a general state as resource. Then a quick reminder is that we should just optimize this quantity, not the entire fidelity, average fidelity. Then by using the general expression, we can show that, our first task is to calculate this scalar product. Then by using the general expression, we can calculate first these, and then by applying performing the unitary operations, we have this. All right, and using these, we can write this scalar product and split it in two parts, a green and a red one. And the very good news for us is that this vector does not depend on T, and this matrix also, that neither. Then if you calculate, if you already calculate our scalar product, we can split our average fidelity tilde in the radial and the directions part. Okay, setting this decomposition of the state, here we have the direction and here the modulus. We can use these equalities that I took from this paper of Orotekis, and we have our first result, that is that the purity of your input states is concentrated here in this quantity, and it is not the trace of this matrix. The trace of this matrix does not depend on the purity of your initial states, and this is something good for us at least.
Sorry, please imagine the A, capital A.
Okay. Ooh. Sorry, here. Here we have the general expression for the conditional states that depends on the measurement, and the resource here and here. All right. Here we have the Bloch vector of your initial state. And you can, when you have this expression, you can apply now your unitary operations or your rotations, and your vector, your scalar product can be written as follows. And the good news is that here we haven't T, and neither we haven't T.
Sorry, so A is just this
Oh, yes, yes.
Okay.
A is this
A is
matrix.
yeah, it's somehow-
Sorry.
Okay.
Yes,
So-
yes.
Okay.
And a quick remark, here we have the rotations we have to move in order to reach the maximum. Another remark is the final average fidelity does not depend on vector W. Omega, sorry, omega. Well, now this is our new optimization problem. We have to move this rotation in order to reach the maximum. And it is a hard task if you set general things, set a general von Neumann measurement, set a general resource estates. It is a hard task, at least for me.
I have a question about the wealth case. So I see that there is a 1/2 first term,
Yes.
and all the others. So is it possible that the second large term vanishes and F max is only 1/2? Or is it
Yes.
possible?
Yes.
So what are the conditions that this trace vanishes?
You have to measure.
Sorry, the maximal trace vanishes.
If you measure the computational basis and you prepare a classical quantum state, you obtain 1/2. It is complicated to. Well, we can discuss later because we should do the math. If, for example, if you prepare the no, I should do the math.
And this result is independent of the isentropic distribution, right? You didn't choose, because in the beginning you show a family of isentropic, but you didn't have to choose any. You can
Yes, exactly. This distribution is here. It's concentrated in this number that is defined there.
Okay, now.
Yes, yes. The distribution is in alpha. And if you want to take the maximum, you have to optimize over this rotation.
C's are also dependent on I, on Ri? C's.
C's are the measurement,
Okay.
the covariance matrix of the
You don't
measurement.
need to optimize over them.
No, 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 no. Just the rotation.
CJ or C without index?
CI and T is the transpose operation.
I was wondering whether one index possibly is missing.
No, because we have here one index because we are adding just the possible results of your measurement. We have, for example, if you take a von Neumann measurement and you have 2 qubits, you have 4 different measurement operators conforming your, for example, these are your measurement operators of your P over N.
My question was, what is the difference between C without index and C with index J?
I'm sorry. C without is the covariance matrix of your resource estate, and CI is the covariance matrix of these guys here. Okay, sorry, God. Well, this in general is general a hard task. Then this was already said. We can use. Well, as the purity of your input distribution state is concentrated here and does not play any role in your maximization problem, you can use the known solution for pure states. This is a good news. Let us consider, for example, a standard quantum teleportation. In a standard quantum teleportation, our measurement is a projection onto the Bell states. And we use this result that is the one that states the value or your score, depending on the fully entangled fraction. If we use this, we have the solution for the optimization problem for a standard quantum teleportation and an arbitrary distribution of input states. That is the large equation here. The resource state here, and as we can see, we have a more complex solution. Yes, more complex behavior of your fidelity. Okay, the conditional states are given by these matrices and products. Let's take now a simple set of resource states given by Bell diagonal states. The Bell diagonal states are parameterized by three numbers, C1, C2, C3, belonging to a specific tetrahedron. And the marginal states are maximally mixed, are the identity basically. And the good news here is that for this set of resource states, we know the explicit expression of the fully entangled fraction as a function of the eigenvalues of your resource states. Now, in order to have analytical expression, we take a particular Bell diagonal state that is a Werner one, given by this. Here we have a projection onto one of the Bell states, and the maximal average fidelity holds results given by this equation. And our question is the protocol basically hold the general rule. The protocol is useful only when the resource is entangled, and the short answer is that no. In order to see that, here we have the standard quantum teleportation protocol, the score, maximal average fidelity, and the shaded part is separable states, separable Werner states. Here we have the correlations of the resource. Okay? We are moving the parameter of the correlation of the resource. Exactly. The horizontal line here is the classical average fidelity. The here we are considering the entire block ball. Okay. In this situation, you have this value for your classical average fidelity. Yes. Approximately.
This is like 4 pi over something. No,
yes. I have the analytical expression here. Well, then we have separable state here. Then our new question is, well, here we have no entanglement, but here we have quantum discord. We have a kind of quantum, a relatively new kind of quantum correlations that is called quantum discord like. Then our new question is that if this kind of correlation are responsible for this useful of the protocol, and the short answer is also that no. And then our new question is what's happening here. In order to, this is the demonstration why no. We take a simple set of classical quantum states that can be written as Bell diagonal states, and this kind of states have no quantum correlation of any kind. And if you take as a resource these states, the fidelity always takes this value. C is the parameter, is the new parameter of the correlation. Here is the average fidelity corresponding to these resource states. Here, when I take P equal to C, then we can see that we could have a useful protocol even when the resource has no correlation of any kind, has no quantum correlation of any kind. Then now, yes, the next question is what's happening here? And there is a key point that the Alice measurement, or the characteristical measurement of your protocol, of the standard quantum teleportation protocol, projects onto states that are fully entangled. What happens if we change that measurement? Then we took a more general set of states given by two numbers, L and P. These four states depend on two numbers, L, two complex numbers. The entanglement of each one of these states does not depend on the phases of the complex numbers. Correspondingly, we will take real numbers, L and P. And as we want to do a specific task, we will take just one number, L equal to P, because if we do that, we have the same amount of entanglement in these states. And we have one parameter that is parameterizing the correlations. Then it is too easy to do the math. Well, it is important to remark that here, this expression is a monotonous function of the entanglement quantified by the von Neumann entropy. And we will use this expression to move the measurement and move the entanglement of the basis. But this, if we change the measurement, this protocol is not a standard Qt. Correspondingly, we should face another optimization problem. The good news is that if you take as resource state the classical quantum if you take as resource the Bell diagonal states, you can rewrite your optimization problem as the same as this protocol, standard quantum teleportation, if you change your resource suitably, taking this new resource. Quick reminder, Cn here quantify entanglement. If Cn is 0, then you have the computational basis, and if Cn is 1, you have the Bell basis. Well, let's take now the known situation that is pure states. If we take pure states, the general maximal average fidelity takes this expression. And here we have the volume of the sets. You have the volume of those vectors C1, C2, C3 that correspond to a non-useful protocol. As we said before, if we take the Bell basis, taking Cn equal to 1, and you teleport pure states, then your non-useful states are the separable one. This is the set of Bell diagonal states that has no entanglement.
This is octahedron.
Yes, yes. And these vectors, if all Bell diagonal states form this, a tetrahedron. And this is the computational basis. This means that if you take the computational basis, no correlation in the measurement, all your resources are non-useful. All right. Well, if you increase the entanglement in the measurement, if you decrease the entanglement in your measurement, then your volume is greater.
So you get something like truncated tetrahedrons, yes, of different.
Yes, yes.
And
Yes, this is an interesting set. Well, let's move. Yes.
In this, let's say, first example on the left down, you have some like 4 triangles and 4 hexagons, non-regular.
Yes, I think that yes. I haven't analyzed the shapes of the, but I think that yes, because it is this figure being greater. I don't know. I think that I should analyze better.
So I think they are called Archimedean pointers.
Okay. Okay. Well, how are we with the time? Ooh.
Yes, so we need something like this.
Yes. I finished. Well, let's take then completely random. You want to teleport all the block ball, completely random states. As we saw before, here is the maximal average fidelity for the standard quantum teleportation protocol, because here Cn is 1. Here we have the Bell basis, and this axis corresponds to the correlation of your resource. Then, if you take measurements with lower quantum entanglement, then your score is lower also. But it's surprised that you can take separable states. It is surprising that if you take separable states that are here and take lower values on your measurement, you still have a lot of useful protocol. And well, you can do here. We are taking off the entanglement of the measurement, and here we have classical quantum states as resource. Well, I think that I will finish now. Okay, that's all. Thank you for listening.
Okay, thank you very much. Yes, so thank you for finishing ahead of time. So we have a lot of time for discussion. Now let me check. Are you around? Is there somebody? Oh, do you know what they can see now? Can you see?
Yeah. Yes.
Yes.
Okay, so can you can you say something? Is there somebody from external world who would like to ask a question?
Send a question to the chat.
Yes, but can you hear somebody? Please unmute.
Pedro Lamberti has his. Oh.
Yes, but Pedro, can you unmute yourself and try to say something?
Maybe I can ask a question that you while they get some correct.
Just a second. But have you Pedro wrote something?
No, Roberto Salazar wrote that he has no questions.
Okay, so now Patrick has a question.
So you said something about the fact that you can have improvement when there are no quantum correlations, also no quantum discord, and then, but it's still not a situation that is simulable by some classical situation, right? Because you overcome two facts. So can you just one more time repeat this argument? You said that when you make the measurements, you then prepare maximally entangled state or something when you do those corrections?
Yes.
Where is the quantumness?
Yes, totally. Then we have in the quantum teleportation protocol, we have two ingredients, the measurement and the resource. If you consider a distribution which could include mixed states, for example, let's take the more greater, you have a random mixed states. And you take the measurement as the Bell basis. Here we have a full entanglement. You can overcome the classical fidelity, taking a resource that is a classical quantum state. This state has no quantum correlation of any kind, but it has classical correlation. If you take off the classical correlation, you have not a useful protocol. You need the classical correlation here.
The classical teleportation, you also can have correlations, right? I mean, you can also have classical correlations in the classical. You can have some random shared bits.
Yes.
And then you still get over it. So
yes, it is very good your question. What was our next step? Was to consider another basis and taking off the entanglements. And well, our result was that you have lower scores if you take off the measurement. Our conclusion is that your correlations, the most important correlation of the quantum teleportation protocol are in the measurements. Is
at least for mixed states, because for pure states it doesn't.
Exactly, totally. What is the next step? Here we are using a sense of distinguishability. Here we are using fidelity. What happens if we change the distance? Or are these results conserved or not if you use another distance? That's a very good question, but that's a lot of work because you have to do the classical part also.
Yes, but for qubits fidelity, like for two-level systems, fidelity is like pretty easily related
Yes.
to all other things, right? Because there's a special,
Yes.
Okay. Thanks a lot.
Oliver.
Could you repeat where this 2/3 number comes from? It's the
2/3 is for the classical protocol and a distribution of pure states.
It comes somehow from Alice making a measurement on her qubit and communicating what she got to Bob and Bob preparing what she got.
That's the game.
It's only for states, right? So should it be surprising that you can beat it when you allow mixed states as inputs? Right? In some sense, adding mixed states as inputs gives you.
He was comparing with the not 2/3. He was comparing with 0.811, which was the classical for mixed states.
When you change the distribution, you change all. You have to change the classical and the quantum part.
Okay, so 0.811 is what we're comparing.
Exactly.
And the best fidelity you can do with the classical protocol when your inputs in the form of the log.
Exactly.
And maybe just one final question here.
Yes.
So this is just with numbers to remember. So this is 0.811 for classical one. And what do you get when you get this? When you use this?
The shell, for example.
No, not shell. When you use the state that has no, like this Werner states with 1/3, like the one that has no correlations. You get this region when you said like T from 0 to 1/3 was no quantum correlations, and then from 1/3 up. So what was like? What's the best improvement you can get while you still don't have any quantum stuff?
That's a very good.
Yeah, somewhere.
No, before. Here we had separable.
Okay, so it's a little bit up. Okay,
1/3. Here we have P equal to 1/3.
Yeah.
And here we have classical quantum states.
Okay, I see.
Here we have maximal classical correlation of on the reason.
Cool, thanks.
Thank you very much.